As I mentioned in the previous video, there are several tests to determine convergence or divergence of a given series. One of the basic ones is called the divergence test. Suppose we have a series sigma an, and can start from any integer, let's say 1. It could be from 0 or any other integer up to infinity. And this, as we know, means A1 plus A2 plus A3. And we have infinitely many terms. If the limit of the general term, if the limit of an as n tends to infinity is not equal to 0, then for sure the series is divergent. But if it is equal to 0, we cannot say anything based on the divergence test. The divergence test is inconclusive, meaning that we cannot get any results. So if the limit of the general term as n tends to infinity happens to be 0, then the divergence test is the divergence test is inconclusive, meaning that we cannot make any conclusion on the convergence or divergence of the series based on the divergence test. So we need other tests to determine the convergence or divergence. So if, let me repeat, if the limit of the general term is not equal to 0, then the series for sure is divergent. But if the limit is equal to 0, the divergence test cannot give us any information. We need other tests that we are going to discuss later to determine convergence or divergence of a series. Let's see an example. Sigma of n plus 2 over n plus 5 as n runs from 1 to infinity. So I want to use the divergence test. So I want to use the divergence test to see that if the divergence test tells us it is divergent or divergence test is inconclusive and we need some other test. So the general term is n plus 2 over n plus 5. And we find the limit as n tends to infinity. As you have seen before when we discussed the limit of such terms, we just keep the expression with the highest power from the top and the term with the highest power at the bottom, and n over n is 1, and this is not 0. So based on the divergence test, for sure we can say that sigma of n plus 2 over n plus 5 is divergent. If in an example this happens to be equal to 0, this limit is 0, then the divergence test doesn't give us any information. We need some other test to determine convergence or divergence. In many cases, the limit is equal to zero, so the divergence test is not conclusive, or in other words, it is inconclusive, and we need another test. One of the other tests that we mention here, and we use it to obtain a very useful test, is the integral test. In fact, in the integral test, under the conditions that I'm gonna write down, the convergence or divergence of the series depends on the convergence or divergence of the associated integral. Let's see how it works. So suppose sigma an, again, n can start from any integer, like say 1, and from 1 to infinity. Instead of n, we can use any other letter, k, j, i, whatever letter that you would like to, you can use. Suppose sigma an, this be a series with positive terms. So all the ANs are positive numbers. Also, let f of x be a continuous decreasing function over the interval from 1 to plus infinity, such that at every n, f of n is equal to an, such that for every n, f of n equals an. This means that when n is 1, f of 1 is a1, f of 2 is a2, so on and so forth. Then, based on these assumptions, if this integral from 1 to infinity of f of x dx is convergent, then that series an is convergent. And if this integral from 1 to infinity of f of x dx is divergent, then the integral of, then this series sigma of an is divergent. So the convergence or divergence of the series under these assumptions will be dependent on the convergence or divergence of the corresponding integral. To clarify this, let's see a couple of examples. For sigma of 1 over n runs from 1 to infinity. As I mentioned in the previous meeting, it's called the harmonic series. Let's see the harmonic series, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on and so forth. I want to see that whether this, using the integral test, this is convergent or divergent. So let me erase these. Use the integral test to determine convergence or divergence of sigma of 1 over a. So what function do you suggest that we use here and find the integral to see that whether that integral is convergent or divergent? Obviously, the function that we have, since at any n, that function should be equal to 1 over n, so f of x is 1 over x. So to use the integral test, I just integrate a 1 over x over the interval from 1 to infinity. If this integral happens to be convergent, we can conclude the series is convergent. If this integral happens to be divergent, then the series is divergent. I'm just following this integral test. Do you remember for this improper integral how we did this? As you might remember, we calculated this as follows. The integral from 1 to b, and then we let b tend to infinity of 1 over x dx. The limit as b tends to infinity. Antiderivative of 1 over x is ln of x. It should be evaluated at the limit numbers of the integral. I didn't use the absolute value because the interval is from 1 to infinity. We don't meet any negative number from 1 to infinity. So this equals the limit as b tends to infinity. Evaluation of ln of x at b is ln of b, at 1 is ln of 1. But we know that the logarithm of b as b tends to infinity is equal to infinity. So this is the limit of this is infinity. So the integral is infinity, which is divergent. Therefore, by the integral test, this series is also divergent. So using the integral test, we could conclude that this is divergent. If I wanted to use the divergence test, the limit of 1 over n as n tends to infinity is 0. And when the limit of the general term is 0, the divergence test is inconclusive. It doesn't give me any information about convergence or divergence. That's why here I use the integral test. In the next example, sigma of 1 over n squared and runs from 1 to infinity. So use the integral test. Use the integral test to determine convergence or divergence of sigma of 1 over n squared. So what function do you consider to integrate? Since at any n it should give me 1 over n squared, the decreasing function of 1 over x squared is the function that we integrate to see that whether it is convergent or divergent. So that's the integral that we do. We have done this integral before in the discussion of improper integrals, but let me repeat this here. Let's see if this improper integral is a finite number, which means convergent, or it is not a finite number, so that will be divergent. Antiderivative of 1 over x squared is negative 1 over x, and then we evaluate at the limits of the integral. So this equals the limit as b tends to infinity. Evaluation of minus 1 over x at b is minus 1 over b, minus evaluation at 1 is minus 1 over 1. Now, as b tends to infinity, this is going to be 0. 1 divided by infinity is 0. And minus minus 1 in the next parenthesis is going to be 1. So this is a convergent integral. Therefore, by the integral test, this series is also convergent. Since that improper integral was equal to a number, the series is also equal to a finite number, although that finite number is not necessarily 1, it's a different number. Here, just that integral test claims that uh, if the corresponding integral is convergent, the series is convergent as well. If the corresponding integral is divergent, the series is divergent too. Next example, sigma of 1 over radical n, or n to the power of 1 half. This is radical n, or n to the power of 1 half, as n rounds from 1 to infinity. So 1 over n to the power of 1 half. So use the integral test and determine whether this series is convergent or divergent. So what function would you consider for this series to integrate? F of x is 1 over x to the power of 1 half, or 1 over radical x. So I look at the integral from 1 to infinity of 1 over x to the power of 1 half dx. This is an improper integral. The way that we deal with this is we'll find the limit as b tends to infinity of the integral from 1 to b of 1 over x to the power of 1 half dx. 1 over x to the power of 1 half is like x to minus 1 half. So if I move x to 1 half from denominator to the top, it becomes x to minus 1 half. So the limit as b tends to infinity. Antiderivative of x to minus 1 half using the power rule is x to the power of minus 1 half plus 1, which is 1 half, divided by 1 half. Dividing by 1 half is the same as multiplying by 2. So, and this should be evaluated at the limits of the integral. And we should do the subtraction. So the limit as b tends to infinity 2 times x to the power of 1 half evaluated at b is 2 to the power of b to the power of 1 half, which is 2 times radical b. So b to the power of 1 half is the same as radical b minus that function 2 times x to the power of 1 half evaluated at 1 is 2 times 1 to the power of 1 half is 1, so 2 times that is 2. One more time, this antiderivative 2 times x to the power of 1 half evaluated at b is 2 times b to the power of 1 half, and we know that b to the power of 1 half is radical b. And the same function evaluated at 1 is 2 times 1 to the power of 1 half, which is 2. When b tends to infinity, radical b is going to be infinity, right? So radical infinity is going to be infinity. And 2 times infinity minus 2 is infinity, meaning that the integral is divergent. Therefore, by the integral test, the corresponding series sigma of 1 over radical n, or 1 over n to the power of 1 half, is also divergent. Based on these last three examples, 1 over n, 1 over n squared, 1 over n to the power of 1 half, maybe you have guessed that when the power of n in the denominator is more than 1, like here, the series is convergent. And when it is 1, like here, the power of n in the denominator is 1, or here, the power of n in the denominator is 1 half, the series is divergent. In fact, this is called the p-series test. The p-series test. So if p is more than 1, then sigma of 1 over n to the power of p, and runs from 1 to infinity, is convergence. And if p is less than or equal to 1, this series of 1 over n to the power of p is divergent. So the last three examples, we could have explained the divergence or convergence by using the p-series test. Let's see some examples. Sigma of 1 over n to the power of 5 and runs from 1 to infinity. So you use the I want to use the p-series test and determine convergence or divergence. This is the p-series, and so this is a p-series. What is p in this example? With p equals that exponent of n is 5. That test says that if p is more than 1, then the p-series is convergent. 5 is more than 1. Therefore, by the p-series test, sigma of 1 over n to the power of p and runs from 1 to infinity is convergence because that p is 5 and is more than 1. As usual, please try the next example on your own. Sigma of 1 over cube root of, instead of n, let me use another letter, k. K squared, and k runs from 1 to infinity. In the examples so far today, I used the letter n, but of course I can use any other letter, like here I've used k. So how do you use the p-series test to determine the convergence or divergence of these series? First of all, this series, in fact, when I look at this, is sigma of 1 over k to which power? Using basic algebra, it is k to the power of 2/3. So this is a p-series with p is what? 2/3. Is 2/3 more than 1 or less than 1? It is less than 1. Therefore, I can conclude that the sigma of 1 over cube root of k squared is divergent based on the p-series test. Let me do another example. By the way, in this example, the numerator was 1. It could be any other number, the numerator. It doesn't affect the uh, convergence or divergence because the number can be pulled out, right? So suppose I have sigma of, say, 6 over cube root of k to the 4. Is this convergent or divergence? And how do you use p-series test? First of all, notice that since all the terms have 6, this is like, by the way, k runs from 1 to infinity. Since all the terms have 6 in common, it's like I can factor 6 out. 1 over cube root of k to the 4. So that 6 doesn't affect the nature of convergence or divergence of this series. So in the denominator, cube root of k to the 4 is what? K to which power? K to the power of 4/3. Now, and this is a p series with p is what? P is 4/3. And by the p series test, if this is more than 1, which 4/3 is the case, is more than 1, we can conclude that this series sigma of 6 over cube root of k to the 4, it runs from 1 to infinity, is convergent by the p series test.